I've stressed that conditional expectation would better be called partial expectation, where we are integrating out the dependence of our random variable on information that is not present in the sigma field that we're conditioning on. So, what if the sigma field we're conditioning on has no information about the random variable? We've seen one example of that, where the sigma field is the minimal sigma field containing only the empty set and the full probability space. But it could be a rich, large sigma field that is independent from our random variable. Then it doesn't have any information about it. As you might intuitively expect, what happens in that case is the same as what happens with the minimal sigma field. If x is a random variable taking values in some measurable space SB, and G is a subsigma field of the domain sigma field that is independent from the sigma field generated by x, then for any function of x that is L1, the conditional expectation of f at x given G is just almost surely the constant expectation of f at x. Moreover, this is yet another way to recognize independence. If it so happens that every bounded measurable function f on the range has the property that the conditional expectation of f at x is just the expectation of f at x almost surely, then we can conclude that the conditioning sigma field G is in fact independent of the random variable. Let's prove that quite quickly. For the forward direction, supposing that these two are independent, let y be any bounded G-measurable random variable. Then since f at x is L1 and y is bounded and therefore L1, since these two are independent from each other, we get factorization of expectations, and this is the expected value of f at x times the expected value of y. Now the expected value of f at x is a constant, and so we can put that constant a back inside the expected value, so this is the expected value of a times y. And what we see is that this G measurable random variable, this constant, satisfies the averaging property when integrated against any bounded G measurable function, and so we can conclude from there that the conditional expectation given G of x is almost surely equal to a, i.e. equal to the expected value of f at x as we desired. Now for the converse, suppose that what we know is that this property holds for all bounded G-measurable functions f. Well then, by the averaging property, this is equal to the expected value of the conditional expectation of f at x given G times y. By assumption, that conditional expectation is just a constant, so this is the expected value, taking it out, of f at x times the expected value of y. So we see that we get this factorization of expectations for all bounded measurable functions f and bounded measurable y, and it follows from there that sigma of x and G are independent as claimed. Now, let's take a cue from our discussions of independence, where we defined independence of sigma fields, but then immediately imported into independence of random variables. Two random variables were called independent if the sigma fields they generate are independent. Similarly, we'd like to talk about conditioning on a random variable rather than conditioning on a sigma field, and we can do that simply by following the same method. Given a random variable, x, taking values in some measurable space, we could think of that space as Rd with the Borel sigma field, for example, so I've written this as if it were a random vector, and an L1 random variable of a sigma field f, then we can condition y on the sigma field generated by x, which is a subsigma field of the domain sigma field f. Here are our two favorite notations for that. We've been favoring this one, but we'll shortly be moving towards this notation as our standard, because we're going to give this special notation now. If we are conditioning on the sigma field generated by a random variable x, we will just denote this as the conditional expectation of y given x. Again, all this means is that we are conditioning on the sigma field generated by x, and we have a lot of machinery for understanding that. But we get an extra bonus here. This random variable is an L1 random variable measurable with respect to the sigma field generated by x. But we know what functions measurable with respect to this sigma field look like. By the Doob-Dinkin representation, any such random variable is just a function of x. And so this conditional expectation is going to be some y-dependent function of x. Now, to compute the conditional expectation, we just need to find out what that function is. So we have some notation for it, and this can be a little confusing, but the notation is the function of the range space S here that we can compose with x to get this conditional expectation is denoted as the conditional expectation of y given that x equals s. That is, its value at s. Now I want to emphasize that this does not make literal sense unless the event that x equals s has positive probability. If that event has positive probability, then this has a well-defined meaning. That would be the expected value of y times the indicator that x equals s divided by the probability that x equals s. However, this is only meaningful if this denominator is strictly positive, and we will largely be working with random variables that do not have positive probabilities of attaining any particular value. So we cannot make sense of this in general. However, we can make sense of this. It's just defined to be the function which exists here by the Doob-Dinkin representation and is unique at least on the range of x. In the special case where this is a positive probability event, it's an easy exercise to check that in fact this is a correct formula for the value of that function on a such range point s. Now let's combine our tools for understanding conditional expectation with this new formulation. The averaging property for conditional expectation says that the conditional expectation, which we now know is this function of x, is uniquely defined by this property here, where we integrate against any bounded g measurable function here. G in this case is sigma of x, and so again by Doob-Dinkin, we know that any bounded measurable function is some bounded function of x. And so here, again, we have a nice simplification of the averaging property. The conditional expectation of y given x is this function of x, uniquely determined by this property here, ranging over all bounded functions of the range. So in particular, if we were to take the function h to be the indicator function of the singleton s, then the left-hand side is the expected value of y times the indicator that x equals s, and the right-hand side is the expected value of fy at s times the indicator of the set where x equals s. But since this is just a constant now, this is fy at s times the probability that x equals s. And if this has positive probability, we can divide through to see that indeed this is a correct formula in that case. But generally there isn't such a simple formula for what this function is. So if our goal is to calculate this function in a particular setting, we need some other tools. And that's what the rest of our discussions about conditional expectation are going to be. For starters, using what we developed on the previous slide, let's see if we can understand what this function looks like in the special case that x and y are independent from each other. Intuitively, if x and y are independent, then y should be a constant with respect to x. We can make that precise as follows. In this case, where I have two random variables, x and y, taking values in two measurable spaces, and they are independent, then if we take any function of the two of them, that is, any, say, bounded, measurable on the product space function of x and y, and we condition on x, that's a typical sort of thing that we're going to want to do. The conditional expectation of f at x and y given x, we can compute exactly what that function is. This function, which remember just means whatever function of capital X this random variable is nothing other than this unconditioned expectation here. That is, we treat x as a constant here, and then take the expected value of this. And just to belabor the point, what we're doing here is computing an integral over the range of y, f at xy, integrated against the law of y. Let's prove this. X and y being independent means that their joint law is the product of their individual marginal distributions. And so if h is any bounded measurable function of the range S of x, then we can compute this expected value here that we're going to need to use the averaging property to identify the conditional expectation. It's just, by the change of variables theorem, the double integral over s times t of f at little x little y, h at x, times this product joint law, mu x times mu y, of dx dy. Well, now we'll use Fubini's theorem to separate that out as an iterated integral, and we'll first integrate with respect to x. We can pull out the h of x, which doesn't depend on y, and on the inside, we'll integrate with respect to y. Now, this inside integral here is exactly the thing we're looking for, this expectation holding little x constant. So let's call that fy of little x. And so, in other words, by Fubini's theorem, this is equal to the integral over s of fy at x, h of x, mu x of dx. And again, by the change of variables formula, that's the expected value of fy at capital X times h of x. And so we see that for every bounded function h of the range, this expectation is equal to this expectation. This is a function that is measurable with respect to sigma of x as we need. And so by the averaging property, we've identified this as equal to this, which is exactly the statement that we were trying to prove. Great, so we now have a precise statement that y is a constant with respect to x, or x is a constant with respect to y, when x and y are independent from each other. And that gives us a very nice, easy to compute formula for this conditional expectation of f at xy, given that x equals particular value, little x, even in the case where we can't actually divide by the probability of this event. But it's important to note that this particular formula here for that function holds if and only if x and y are independent from each other. We would like to be able to say something about this function in much greater generality. So to start down that road, let's not assume independence, but at least assume some nice regularity of these random variables. Suppose that x and y have a joint density. Now, to keep things simple here, I'm just going to assume that x and y are real valued, so xy is a random vector in R2, but this will work in much greater generality as long as there is a joint density for random vectors x and y, as we'll see a little bit later. We want to identify this conditional expectation of a function of x and y conditioned on x, which is some function, I'll just call it g of x. We want to identify that function g. Well, that means that we want to, for each bounded Borel measurable function h, find the function g of x here, so that if I integrate that against h of x, I get this. Let's just write everything out in terms of their densities. So this is the integral of g of little x, h of little x, integrated against the law of capital X. And on the right-hand side, this is the double integral of f at little xy, h at x, times the joint law of x and y, which is rho of xy dx dy. Now, since x and y have a joint density, that means that each of x and y has a marginal density, which we can compute by integrating out the other variable, which should sound familiar from the last lecture. That is to say, the probability that x is in some Borel set A is the same as the probability that the vector xy is in A times R. and that's the integral over a times r of this joint density, which by Fubini's theorem, or actually just Tonelli's theorem here, is the integral over a of this partial integral of rho. And that means that the density of x is given by that partial integral right there. And so we can replace the left-hand side here with the integral of h of x, g of x, times that partial integral, rho x dx. And we can rewrite the right-hand side as the integral of h of x times this inside integral with respect to dy of f at xy, rho of xy, with a dx on the outside. We want to find a function g that will make this true for every h, and the formula tells us exactly how to do that just by dividing through by rho x. So let's now state that as a proposition. If x and y have a joint density, and if we let rho x denote the marginal density of x just by integrating out y in the joint density, then we can define the conditional density of y given x, which is usually written like this, and it's just defined to be the ratio of the joint density divided by x's marginal density. Of course, there's a bit of a problem here. No one said that this was going to be a non-zero function. In fact, it could be zero on big swaths of the real line. So let's take care of that by also zeroing it out whenever it takes the value 0. And it could also blow up at a small set of points, so let's also zero it out at those points as well. This is the conditional density of y given x, basically just this ratio. And what we have basically just shown on the previous slide is that if we have any, say, bounded function of two variables, then the conditional expectation of f at x and y given x is g at x, where g is the integral of f against the conditional density of y given x. So as we saw on the last slide, we showed that this will hold using the averaging property for conditional expectation, provided that our function g satisfies this identity here. And so this ratio for the definition of g makes that true, except that we have to be careful about this zeroing out. We need this equation to stay true even when rho of x equals 0. So that means that if this is actually going to work out, it better be true that for any x where rho x of 0, the right-hand side is 0 as well. And that's true. If rho of x at a point little x is 0, then the integral of f at xy times the joint density of capital X and capital Y integrated against y is also 0. And that's simply because the absolute value of this by the triangle inequality is less than or equal to the supremum over y of f at x and y taken outside the integral times the integral of the absolute value of rho of x and y integrated against y. But we don't need that absolute value in there because that is a probability density and is therefore positive. And that integral is exactly rho of x, which we decided was 0. And that means that this is 0. So there we have a nice formula. The conditional expectation of f at xy given x is this function of little x. In other words, the conditional expectation of f at x and y, given that capital X equals little x, is equal to this integral here, which is something that we can in principle compute explicitly. And it's a fun little exercise to now show what happens in the case where x and y are independent and recover the previous result in the special regular case we're dealing with here. Now, this is a ubiquitous formula that you'll see in all kinds of probability and statistics textbooks, and we will certainly make use of it in our foregoing discussions of stochastic processes. But I do want to note that it fundamentally requires the regularity of the random vector xy having a joint density, which is not something we're always going to want to assume. Our next goal is to develop some new probabilistic constructs that we can use in place of this simple formula to give a general description of this conditional expectation, even in the case where x and y do not have a joint density. And that's going to lead us to a discussion of probability kernels.